is the second session, and now we try to generalize this whole concept, which is very interesting actually. In fact, this is how seemingly unrelated topics and the techniques that you use lead to very nice general result. Now this is a sort of prelude to the so-called Brouwer's fixed point theorem. And in fact, you know that fixed point theorems are extremely powerful to prove the existence of solutions of several types of solutions. I'll just start with something which is very much known to you. Let us consider the following problem. Suppose you have a real value function or some interval. Now what we want to, so the question that you ask is this: does there exist a 0 of f? That means, does there exist x belonging to R such that fx equal to 0? Now what we do is, this as such is a difficult problem, even to prove the existence, and to compute it still worse. And there may be several zeros for the function, or there may be no zero at all for this function. And the questions arise: when do this particular function has a zero? What one does is this: first stage is convert this problem into a new problem. So what you do is define fx minus x or fx plus x. Okay. Now you see that fx equal to 0 if and only if that's a nice conversion of this problem. Therefore, instead of asking questions on this, we will now start working with this. That means now we look at this problem. We look at this problem as, now you see that G is a map from R to R, and we are asking the following question: does there exist a x belonging to R which is left invariant by G. Okay? Or if you look at this problem in the form of a graph, suppose you draw the graph of this function, something like this. Then what is this problem? Suppose this is y equal to gx or x gx we are plotting. Now you see that y equal to x you plot. Now you see this is the point, say x tilde, say, then you have gx tilde, or geometrically you are asking another question, namely whether the graph of the function g intersects the line y equal to x. This is the question that you are asking. Okay, fine. Now it is quite possible that this function does not intersect this line at all. Okay. Secondly, it may be the case that it intersects at more than one point. Okay. Accordingly, there exists no solution at all, or there exists several solutions for this problem. Okay. So the question that you now normally ask is, first of all, does there exist a solution? Then, of course, in many problems you would like to know whether the solution is unique. Okay, so these are the two questions: existence of solution, uniqueness. So if you simply take one G and then work with it, you may not get a solution at all. That's what I said. Okay. For example, if your G is something like this, or you take a line which is parallel to this line, not passing through any point on this, there may be no solution at all. Okay. And therefore, that is our problem. So the problem is now recast as, see, this is a space. So it's a map from a space into itself. Okay. And then you are asking whether there is a fixed point for the map. So the question is, G considered as a map I'll give a very interesting popular version of this theorem, which was very popular in the early 60s. That was a time, the people started working, many people jumped into this particular area of proving fixed point theorems of different types. Yeah. This was called coffee stirring problem. And if I remember correctly, there was an article that came in Scientific American maybe in 66 or 1966 or 67, I am not very sure, because I heard about this problem at the time when I had just joined IIT. That was in the year 1967. So it must be around that. So this appeared in the Scientific American. It may be in the year 66, 67 or 68. I am not very sure. It was called a coffee stirring problem. The problem is this: you have a cup of coffee. Now you stir the whole thing. What happens? You assume the points on the surface gets redistributed. So if this redistributing technique is continuous, what you probably, the question that you ask is there one point which has returned back to the same position after the stirring? Or is there a fixed point for the stirring operation that you have done? Okay. But maybe I think I will give you a much better version of this probably. So you take the stitching frame that you normally use to hold the cloth stretched. You put it inside a frame, and then you have a sort of clamp here to keep the two frames together, and the the cloth is just tightly put in between the two rings. Okay, and you have a screw, something like this, and you would have, those who are familiar with stitching would know this. You would have seen your mother doing some stitching and using this frame for this purpose. Now you see that I suggest the following: instead of a cloth, you take a sort of stretchable surface. Okay, stretchable surface is something like a sort of rubber sheet. Okay. Now stretch it fully in all directions, rather in a nice way, and then hold it. Clamp it in the stretched manner. Okay. Now what you do is you take a pen and mark the boundary of this on the rubber sheet. After that, you release this. When you release this, you see that because it will get relaxed from the stretched position, and you see that this is what you get. So this is the original region that you had, and you see that the boundary that you have marked will take some position like this. So essentially, the points here get mapped into this. So there is a map phi. So if you consider this particular part as a sort of denoted by D, so you have a mapping from phi from D to D. Now, so it's a mapping which throws all the points in D back to D. Okay, and by the way in which we have done it, by stretching the rubber sheet and then releasing it, you see that this is phi is a contraction. Phi is a contraction means what? See, if you take, there is a distance between 2 points x and y, and then there is a distance between phi x and phi y, that is the images of that. So x goes to phi x, y goes to phi y. Originally you had 2 points here, and those 2 points have come closer if it is a contraction. So the condition will be d of phi x less than or equal to sum alpha times d of xy, where alpha is less than 1. So positive ones. Then you say the mapping phi is a contraction. Now, one of the beautiful theorems that you can prove is that if so, there exists a unique such that is, there is a unique fixed point for this map. That's the theorem that you prove, and you just don't know where that point is. This is the famous Brouwer's fixed point theorem. I have not yet said rigorously what are the conditions on D, etc., and how we work with this idea. Okay. Now, how you apply this is now it would easily suggest to you that probably the Picard's approximation also does something like this. Okay, your integral equation yx equal to y naught plus integral x naught to x f t dt. Now this part you can write ay. See, this part you can write as ay. Then what you are asking is for a class of functions defined on does there exist a fixed point question that you are asking. The equation becomes ay equal to y. So you are asking for a fixed point for a. Now once you prove this general theorem, okay, that when a is a contraction on a space with certain restrictions, then you have a unique fixed point. So then the problem gets into that. So we have to set up the right kind of space in which this becomes a map, and this map is a contraction. Once you prove it's a contraction, then it has a unique fixed point. Now that's the strategy. So it's the same thing. See, these are diverse areas from which the same kind of techniques were used. In both these areas, the techniques used was that of bootstrapping or constructing a sequence. So you start with a, so what you have is this. First of all, your space X has to be a metric space. Because you want to talk about contraction. So you want to talk about the distance between 2 points. So XD is a metric space. Okay. So that is one of the primary conditions that you need, because you need the tool to say whether the points are coming closer or falling apart. So XD is a metric space. Secondly, what is our technique? The technique that you use is this. This is your equation. This is what you want to find out. What do you do? We start with y naught, some point in x. Okay. What you want is that a y naught should belong to x. Say then call it y1. Then what do? You apply a y1. So you want a y1 to be in x and y2 you define as a y1 and so on. So a yn a-y-n. So what do you end up with? You end up with a sequence of points xn. Okay. Now under certain assumptions on A, you see that this sequence so you study the convergence of this sequence. Is this a convergent sequence? Okay, right? So how do you normally proceed in a metric space? If you can show that it is a Cauchy sequence, then it would converge in the space provided your space is complete. So we get the necessary assumptions that you need. So assume X is complete. Now your task is simpler because show Cauchy. If you show that Xn is a Cauchy sequence, then you get that there is a point x to which the sequence would converge. Okay. So the procedure is this: you construct the appropriate complete metric space. On which A is a contraction map. So A is a map from X to X, which is a contraction. The contraction is in the sense that distance of AX ay, if you take 2 points x and y in this space, want this to be less than or equal to and xy for every x and y belonging to x, then it's a contraction. Once this is done, then it follows that this is the contraction mapping here. Okay. Now what is the procedure? The procedure is construct a sequence. Construct a sequence which is Cauchy. So you need conditions to assure that the particular sequence is a Cauchy sequence. In the most abstract form, let us first prove this theorem. So I will give a proof of this theorem. Start with x naught arbitrary point. So you start with an x naught arbitrary. Now what about and construct a sequence xn axn. Now you are endowed, the space is endowed with the or the space and the map has the property that this is less than 1. So alpha constant in the contraction map. We are assuming there exists an alpha. Now what we claim is that xn is a Cauchy sequence. Okay, so we prove this. So you compute this. So you see that. Okay. So dx n plus 1, this is equal to d of axn minus 1, and that is less than or equal to alpha of d minus 1. That is straight away, it is there. Okay. So you can, repeat this. Xn can be written as axn minus 1, this as axn minus 2, and then you get alpha square d of xn minus 1, d of xn minus 2. So this is less than or equal to alpha square etc. Now, what you can prove is this. Okay. When our objective is to prove that this is a Cauchy sequence. Okay. So we will compute this. So we take for n less than m, take d dxn xm. This is less than or equal to, see, you can write this as that's simple. And now you can estimate each one of this. You have estimated. So you see that this is less than or equal to c to the power n alpha. You have brought this down to the base point x0 and x1. Okay, and you see that this is less than or equal to so this is the inequality. This is the main inequality that you use. So you can easily see that this implies that xn is Cauchy, because you see that alpha is and since x is complete, where x is x belonging to x, such that is dxn as n tends to infinity. Now we are assuming A is a contraction. Which implies A is continuous is uniformly continuous, which in turn implies that is Ax equal to x. Now we want to assert that there is only one for uniqueness. Uniqueness, suppose then what do we have? D of Ay, which is less than or equal to alpha times, but alpha lies between, this implies dxy equal to, that means x equal to, that is x equal to. This is the fixed point theorem, and this is how you prove it. It's a very simple proof that you have, but it has, this is called a Brouwer's fixed point theorem. Okay? One of the early fixed point theorems of this variety. Now there are a lot of fixed point theorems which has been proved with various assumptions made and suiting to different problems, and unfortunately what happened was it became an industry after some time, and then there were a lot of trivial papers published on this, slight modifications and so on. But it's a very profound result. It's a very profound result in the sense that, in differential equations, especially partial differential equations, in many cases, if you want to prove the existence of a solution in different type of spaces, what one does is that the given differential equation has an equivalent transformation in some appropriate function space, which becomes a contraction. You can prove that there is a unique fixed point, and this is the general strategy that one adopts. Now let us see how we actually make use of this. Now you see, this is at the end of a long evolution. If you see Picard's theorem, when did Picard's approximation theorem appear? It appeared probably, because Picard lived from 1856 to 1941, I believe. And it's somewhere around the turn of the 20th century that he proposed this approximation methods, Picard's approximation method, which is a sort of forerunner for the fixed point theorem. And in fact, the first problem I also that I gave earlier, that you talk about the zeros of a function, that also can be recast into a fixed point problem, and one can use probably the techniques that are available to solve this problem. Okay, now let us come back to our problem and let us see how we are going to prove this. In fact, it's a very small little stroke that we use, you will get the solution. Okay. So what do we do? So let me just set up the particular x that is required for the purpose and so on. So our problem is this. What are the assumptions that you have? F is continuous on D. And x naught, y naught belongs to D. Okay. Then we, as we proved in the case of this one, you take a rectangle S and then from that you construct the rectangle R and so on. Then what you get is you get an H which is the minimum of that's what we started with. So that on the interval mod x minus x naught less than or equal to H, you have a unique solution. Okay, so let us start reformulating it as a fixed point. Now I just slightly modify H. Okay, I am assuming F is Lipschitz. In Y over D with K as the Lipschitz constant. Now what I do is, I have to choose first the appropriate space. So let me write down X as C where I take H to be the minimum of A, B by M and 1 by K. Because after all, it doesn't, there is no loss of generality, because what ultimately we get at the end of proving the existence and uniqueness theorem is a local existence and uniqueness theorem. That means surrounding the interval x naught, there is an interval, or surrounding the point x naught, there is an interval on which a unique solution of the initial value problem exists. Okay, this is what you prove. Now what one does is, you use this formulation that we did. The formulation was this. See, you have the equivalent integral equation, yx equal to y naught so you prove that this particular integral equation has a unique solution, then it is a solution of the initial value problem. Okay, right. So we take this as your x. Now what is your A? A of y you define as y naught plus integral x naught to x So the first question that you ask is this: is A from X to X? This is the admissibility condition. Okay, so that you can construct the sequence starting from some X naught. Okay, so is this a map from X to X? Okay, what is the, see, you want this a metric space. What is D on? So you take this as, see, it's an normally linear space. Norm of F is equal to supremum of okay, take the sup norm on this interval. Okay, then you know that CAB, okay, C, I, is complete. So if you use this as your norm of this on this linear space, then you are getting it a complete non-linear space, which is a complete metric space. Okay, of course linearity has no role to play in this, because we are not assuming our transformation is a linear transformation. Okay, so we take C x naught minus h to x naught plus h with the condition on h, with h chosen in this way, with the sup norm. The norm induces a metric. What is the metric? D of that is the metric. So X with D is your metric space. Okay, it's a complete metric space. So this is your X on which you impose the sup norm, and then this is the metric that you choose. Then X is a complete metric space. Now this is, you ask the question, is A map from X to X? Let us see whether it is true. Okay, so now what is A phi? So let which is equal to y naught plus integral f t dt. That is A phi. Is the question that you have to ask. So it should be defined on the interval x naught minus h to x naught plus h, etc. And the sup norm should be valid for that, etc. So let us compute this. Now you see that see the function, okay, see on this one, if you choose a function, then you see that the mod phi y would be less than mh. That is what you can prove. So you see that a phi so psi minus is less than or equal to integral x naught to x mod the system. And you know that this is less than or equal to m. Okay, therefore this is less than or equal to this is bounded by m, and mod x minus x naught less than or equal to h, therefore this is therefore psi also has the property that x belongs to R. Okay, whenever that is the admissibility. Therefore, you see that the graph of this function lies inside R. If you start with a function phi which has this property, okay, therefore you see that a phi okay. So if you start with a function and apply a, then a phi belongs to x, right? Now let us show that a is a contraction. So how to prove this? It's a small estimate that you make, from which you will get it immediately. So let us estimate this. See, a phi for two functions belonging to this is equal to integral x naught to x f t dt. So you estimate this. At x. Evaluate it at x is okay. This is less than or equal to and this is less than or equal to use the Lipschitz condition. Which is less than or equal to, take the supremum of this. Say t. Then you have got integral kd. Okay. So this is what. So what you have. So let us take the supremum of this over this. Therefore, supremum of, or what you call the distance between a phi is less than or equal to, this is k times mod, in fact I can write here h, the maximum value on the interval, what is that? This is equal to into distance from cell. Now how have we chosen h? So but h is less than equal to minimum of therefore if I choose this as alpha, okay, so let me choose this as alpha. So h is less than minimum of so you choose h as something less than this, h positive but less than this, then you see that this is going to be less than, and then what happens, kh is less than 1, therefore you get Let me choose. And this is less than 1. Then what do you get? Then you have d of is less than or equal to alpha times d of therefore A is a contraction. Which implies there exists a unique solution, unique function let this d y satisfies the Lipschitz condition. The initial value problem. Right. So that's a proof using the contraction mapping principle. I thought of doing this contraction mapping principle mainly to show you how certain specific results in some specific areas are generalized into a larger context. Okay, there are many problems which can be geared into this language, and one could use this powerful theorem to get the unique solution of the particular problem. And I think I'll stop here. Thank you very much.